Welcome to my session, and this is a container cloud session, and I'm Xu Wang, the CTO and the co-founder of Hyper.sh, and this is my only session in this summit. I know if you search in the schedule, you will find two presenters have the name as Xu Wang, but the other one is not me. Yeah, this one. The smaller one is me, and the bigger one is not. And I come from Hyper.sh, and we began as an open source project for the virtualized container since 2015, 2 years ago. And just 2 years ago in the Tokyo Summit, we introduced a multi-tenant Kubernetes distro. That's a prototype. We call it Hypernetes. That's Hyper and with Kubernetes. And last year, we launched a public container cloud based on the Hypernetes, and this is what I will introduce today. And after 1 year operation, we have many lessons learned from the public cloud, including how we set up it and how users use it, and what's the challenge we meet and how we solve them. And so this is my topic, the lesson we learned from that. And in my topic, I will introduce 4 aspects. First of all, I call it container native cloud. So I will explain why I call it how I prevent it to slide down. Okay. I should put it here? Yeah. Okay. Okay, that's fine. Yep. Where is my? Sorry, the laptop just will drop to the ground. So that's another challenge I need to face. And first of all, I will explain why we call it container native cloud, why it's native, and what's the difference from others, why we say others is not native. Yeah, that's quite offensive. And then I will introduce how we build it as a container native cloud, and then I will introduce some use cases thanks to the innovative users, and many use cases actually beyond what we designed it. And then at last we will introduce some challenge we met and how we solved them. And yeah, first of all, I talk about the cloud, the container native cloud. And I don't know if anyone have attended the summit in Austin last year. Oh yeah. I don't know if you remember, there is a panel called "Do Containers Be the First Class Citizen in the Data Center?" Yeah. In that panel, there's I think Tim Hawkins from Kubernetes and someone from Docker and from Mesosphere. Yeah. And they're talking about what about the first-class citizens. And from my point of view, as an audience, I think, and at that time there's no first citizen containers in the cloud. In my mind, I think we should build something, make the container become the first citizen of the cloud. And first of all, it should be implement a container native API instead of you create the VMs with some APIs, and then set up a container scheduling system on top of the VM pools, and then you call the orchestrators, call Kubernetes or call Swarm to launch the containers. Instead of them, I think if in a container native cloud, you should have the cloud APIs directly for the container creation, container destroy, container start, container stop, and launch the containers without to launch VMs or manage a VM pool. And secondly, you should have some container-centric resources, such as currently in many clouds, if you want to have a floating IP, you need bind it to a VM and do power mapping to some containers inside the VMs. And you may apply the security group to the VMs and schedule the correct container to the correct VM with correct security groups. But I think that's partly unnecessary. And you should be able to apply the floating IPs to a container or attach the security group to a specified containers and treat all your clusters as equally. And that's what I mean, the container-centric resources. And the container-based services, and that's quite simple. And if you have all the containers as the first citizen of the clusters, and you should in the cloud, you should be able to just create containers, and then just like a cron job, you may create container at some time and destroy them after it's finished. And you may have the load balancer for the containers and so on. And at last, you may have be able to charge back containers. You know, for the VMs, the life cycle should be often be several hours to several days, and for the containers, that may several seconds for a container. And it should be reasonable. You launch a container and it start the application in the container start maybe in 3 seconds, and it's run for about 10 seconds and it's stopped. Then you pay for what is run and instead of the several hours. And that's about the container native cloud. But why we want it to be container native? I will begin with the famous quote from David Wheeler. And he told us all the problems in the computer science could be solved by another level of indirections. You know, we have the machines in the data centers and create VMs on top of it and deploy containers on the VM clusters. That's all indirections. And there's more indirections than you needed. Actually, you don't need so many indirection layers. But I think maybe the hard problem is how to reduce one extra indirect layers. Yeah, in Boston Summit, Eric introduced and looks delicious club sandwich to us. Yes, I give the YouTube link for the presentation, so you may find a better picture in the videos. And actually, you know, we Chinese don't do sandwich well, but fortunately, I think you don't like your cloud stack infrastructure stack like this sandwich. So, and the too many layers introduce not only the overhead of the resources. You must keep the redundant resource for every layers for the VM pool, you need to have more extra VM for the high availability, and on the container on the hardware, you need some extra management overhead, but also for the operations. When we introduce container to our infrastructure stack, the main purpose of that is you want to make your infrastructure become immutable. That means you can deploy the application with your containers. You don't need to configure it with Puppet, with Chef, or with Ansible. You can just launch them, and if there's anything going wrong, you can just destroy them and relaunch them. But if you have too many indirection layers, you still have a VM pool here. You need to manage the VM with some deployed agents and with some management tools. And if there is something going wrong, you need to fix the VM state. Yeah, that's the indirection layer introduced overhead for it. So that's why we want to remove the indirect layers. And for this goal, we launched our hyper.sh. It's a container native cloud, and you can just register and you can download the hyper client, which works just like the Docker client. You can just run hyperpool to pull an image from the private or public registry. And when you already have the images in the cloud, you can launch it, use hyper-run, and even with some link with some other features, you can do power mapping and do some labels for it, and bind a host name for it, and so on, just like the Docker command line. Actually, you can just think all the hyper.sh cloud like an Docker daemon in the cloud, and you don't need to think which node the container be scheduled to, and how if the container the node is down. That's all handled by the cloud itself. And so that's much like our ideal utility computing the goal is to make it like a common infrastructure for you, and you can just launch your applications. And you don't have the concept of node. You don't need how many physical or virtualized node in the cluster. You just launch the containers, and moreover, you can use the FIP attach and public IP to the containers itself. You can also configure a security group for the containers, and you can deploy the load balancer for the containers, and use your compose file to launch a set of containers and so on. And this is what we do in the hyper.sh. And I think the most contribution from the hyper.sh is we try to remove the idea of the concept of the VM pool. You don't need to have the concept of something cluster. You don't need to create a cluster for it. But how we do it, then I will have some introduction for how we build this. Yeah, and this is the whole architecture of the hyper.sh backend. And at the most the left side, it's an API router. We use this API router to implement actually it's a Docker APIs, and we open source our client. That's based on the Docker client. Just add some authentication for our cloud, and remove some or add some small features from it. this API router implement the Docker APIs and the life cycle management, such like not in the Kubernetes. In Kubernetes, they don't want to maintain a global state machine for the containers. So the containers have only two states. If it exists, then it's running, and if it's not running, then it's deleted. That's in the Kubernetes. But in the hyper.sh, we let you know your container could be created without started. And once it's stopped, you can keep it, and maybe for some time you may restart it. And for the stopped container, you may commit it to images and so on. So this lifecycle is implemented in the API router and with the Kubernetes itself as the backend. And in the backend, we also introduced some controller to first is we are a multi-tenant system that use the Keystone to do the multi-tenant authentications and tenant management, and they use the Neutron for the multi-tenant network. In the simple Kubernetes network model, you may have all the nodes connected to each other, but for a public cloud, you need to make every user have an independent layer 2 network, just like the VPC in the AWS. And so we use Neutron to do this work, and also we have cinders for the volumes. User may create volumes and insert volumes in their containers. And in the blue. The blue frame, we have open source it. That's originally we call it Kubernetes. We launched it in about 2 years ago for the first alpha version. And in this year, we changed it to StackKube and working on contribute it to OpenStack Foundation, and it's called StackKube. And in Boston Summit, my colleague Harry Zhang have introduced this one, and today I will give some updates about it. And at the bottom of it, we have a distributed graph engine by ourselves. Then you can it persists all the container images and the container root.fs. So if there is some physical node down, you can just launch the containers again on the other node, and that's transparent to the users. If the users specify restart OS, then whatever, if the container fails itself or the node fails, it will always be restarted by the scheduling system. And on the top of the figure, the high level application engines include Compose engine that's you can use the Docker Compose file to launch your applications, and cron engine you can have some timely jobs. Many users will use it. Someone just to do every 5 minutes they launch a container, do some checkpoint, and after the checkpoint done, the container will down itself and be removed, and only the runtime will be charged. And the service engine is for the load balancing. It's just derived from the concept of the Docker service and the Kubernetes service. Actually, it's a load balancer, and all the containers with specified label will be work at the back end of the load balancer. And the Hyperfunc is a serverless engine that if you have an incoming calls, it will create a container, run it to serve the incoming calls and feedback and give feedback, and the containers will done. And that's quite like some should be, maybe used for some hook-like service workload. And in the blue frame and the red button corner as our Hyper-D and Run-V, the virtualized container engine, and that's our secure container engine, and that's why we can launch the container without the VM layer. And you know, for the containers, you always run all the containers inside namespace and on top of a kernel, either VM kernel or host kernel. Actually, for the cloud usage, for the security concern, you have to run the containers from the different user or even different application in different VMs, because that's by some means you need some isolation provided by the hypervisor. You know, in the I think in 2015 in the LinuxCon in Seattle, Linux have an interview about security problem, especially for the C group and the namespace security. And Linux have a very strict view. He said he point out almost all the security problem. Actually, it's about bugs. And even we have a well-designed security framework, some bugs may make it trivial. So you need another level of the encapsulation and use some smaller attack surface to make it more secure. That's why people run a container inside a VM. And at the beginning, the container architecture, only the namespace on the kernel and the applications inside namespace, it looks very simple. But in the cloud practical, everyone uses it in the host kernel and the hypervisor and the virtual machines and the kernel of virtual machines and namespace and VM inside it, and that's introduced too many layers, make it not simple again, not simple anymore. And this is what we proposed in the right side. We use the hypervisor as a button, and we have a small and simple VM here, and we have a kernel, guest kernel inside the VMs, and we just launch the application on top of the kernels instead of a whole operating system. That's make it quite simple, and it's actually it's a lightweight VMs, and from the applications view, it's just like a container. So. Our containers is isolated by the hypervisor, and we are working on make it secure as VM but fast as containers. That's our main idea about the Run-V and the Hyper-D project. And actually, we can do really well on the boot performance of the hyper container itself. So this is a command line of the hyper container itself, not the hyper.sh cloud. In the hyper container on the single machine, you can do it in about 100 milliseconds to launch a container. This is the from you type the command line until the container application started. This is about less than 150 milliseconds, and all these tests is in the small box that not in powerful servers. So that's pretty fast for it.
This is just with Hyper-D without going through stack cube, right?
Yes. As I mentioned, this is only the Hyper-D itself on the single machine and not for the whole project, because for the whole project you need to do some. I think most time-consuming jobs are two points. One is you need to prepare the network, set up all the network for the containers, and the other is if you use a distributed storage for the container image, that may introduce some other overhead. But for the container engine itself, could be quite fast. And I will talk about some the other time consumptions later. Yeah. And until this September, we released version 1.0 for the Run V, and it includes the compatible with the OCI runtime spec 1.0 and the full support of the Kubernetes CRI semantics. Actually, the CRI interface. Some of our engineers are the main contributors, one of the main contributors of the CRI interface itself. So we have the full support of its semantics and support both not only the Intel x86 and also some ARM64 and Power and S390X. And we also support you to use the KVM QEMU and then full virtualization and parallel virtualization and KVM tool. And along all these hypervisor methods, I'd like to say the QEMU and ZenPV works really fast, and others are also supported. And our contributors not only our HyperHQ but also Huawei and Zhejiang University and Intel and Alibaba and IBM and so on. I think the Power and the S390X are contributed by IBM, and for Intel, that's pretty special. You know, maybe someone have visited the Intel booth and they have introduced clear container technologies, and they are clear container and our Run V and Hyper-D are quite similar. Actually, we launched Hyper-D and Intel launched the clear container in the same month. I think it's May 2015. And we have almost the same goal to use the virtualized technology, make the containers have better isolation, and we can use some mature technology for the VMs, especially developed for the NFV and for others. And so we have some actually in the past 2 years we have many discussions with each other, and we share many protocols and many things, and in the clear container 2.1 they just use our init program in the guest VM Hyperstart as their VM guest agent, and then in the 3.0 they have also used our protocol, and we have joined to develop the next generation of the agent inside VM, and we use new protocol. And actually, in this, I think by the end of this month, we will announce more collaboration on this project, and we will introduce this in the KubeCon next month. And the Run V is worked for the Hyper-D and the Container-D and the Cryo that could be connect with the Kubernetes to provide the multi-tenant Kubernetes, and actually they are one of the officially supported or made runtimes for container for the Kubernetes, and the StackKube, I think Harry have introduced this in May in the Boston Summit. And this is the same picture for it. And there is a Kubernetes master to schedule all the node, and include some node include the OpenStack masters. And in OpenStack masters there are Keystone and Cinder and the Neutron servers, and the Neutron and the Keystone will be called by the third-party resource TPR to do some container networking. And on the Kubernetes side, we have another project, Fracty, and that called either Hyper-D or the Docker to create the different containers. And the Fracty will also use the Cinder and the Neutron as the multi-tenant network and multi-tenant volumes. And it could, for the Fracty, it could just insert the block device to the container itself, and instead of use some file system mapping. And that's the whole architecture of the stack kube. And in the stack kube repo includes some the plugins from the OpenStack to the Kubernetes, and it includes some deployment scripts and documentations. And this is the stack kube repo, and you can just check it from the OpenStack/stack kube. And the project status now it's 1.0 beta and in test. And actually, we tested it not only on the x86, but also on ARM64, and all the run well and works. It could support all the Keystone version 2 protocol for the authentication and other tenant management, and support Neutron from the CNI or other interface. Actually, it's also support other network mechanisms, and it supports Cinder to provide the block device and the DNS plugins and the container all the containerized plugins. So this is the current status of the stack kube. It could be used for evaluation. Yeah. And then I have some user side innovation, and the user always do something much beyond our expectation. And first, this is what we expected, and user will do some continual integration workload with Hyper and Buildbot and Jenkins and Drone and some others. And for the container-based CI, you don't need to the preparation and clean up time. You just once you have job, you just launch the job inside the container, and don't need to have some agent and to boot up it. And once the job is done, you can just destroy the container. You don't need some pooling or some scheduling. You just throw the job on top of the cloud. And currently, I think the Buildbot have used the Hyper backend for their own continuous integration. And for us, for our open source project, we also use the Jenkins integration for our own integration test. And this is the continuous integration use case, and it's quite simple. But another one is to use the parallel containers, and because user could just because the preparation of the application in container could be quite short, so you can just launch as many containers as you need, and to do the work in parallel. And then all the container will be spawned and run. And in this case, sometimes you don't it's not only for that it's parallel, but also for some case, some users previously they use one VM and to do some very long job, to do some batch job, maybe every hour or every several hours they have a VM and to launch the job and pull all the data and do some data process because they think they don't need too many. They will fill all the time slot of one VM and with the jobs, and then the job will last for a long time. But with containers, they could just launch several containers to do the job in parallel, and maybe it could finish in 1 or 5 minutes or even less. And then they could have not only have the job done in parallel, but and save their money, but also it can make the job close to real time. So that's their cases, and also the timeline. Some users periodically launch the containers, and inspired by these users, we create a new service called cron, can help users to create the containers automatically, and that's the innovation from the user and not from us. We just implement it and let it become easier to use. And this is the parallel containers, and some users also use it for disaster recovery, and that's really beyond our expectation. Because we can launch the containers in 3 to 5 seconds, so some users use container in their private cloud for their own website, and once their own data center have some problems, they can just launch the containers in our cloud as a disaster recovery, disaster backup, and at this case, they don't need to do something hot standby. They just do cold standby, because if you use the VM for standby, you must have it to do like a hot standby, because it cannot be provisioned in 3 or 5 seconds. You need to keep it running as the hot standby for the high availability. But for a container cloud that could launch the container in maybe in 3 seconds, then you don't need to maintain a hot standby version of your site. You just launch it when you need to recover your site. So that's this is not designed by us. We don't suggest this practice, but the user use it and it looks great. So thanks to the users. And these are all some main contribution from the users, and we actually the users use this for there's some conclusions. They can eliminate the visible resource pooling. Just use the cloud as a pool, and they don't need to manage the pool by themselves. And there is shorter preparation time, so it's more friendly for the parallel jobs, and you can spawn it on demand and meet your standby. And all the containers have their independent life cycle. That is make the management quite simpler than before. And at the end, there is some challenges. The first one is the concurrent launch, because there's much more containers than traditional VMs. So the challenge, there's 2 challenges. Each is for the scheduler for the service load, and the other one is for the creation and the cleanup of the resources. So we create a new scheduler plugin to matrix the concurrency and to schedule to reduce to make them have all the nodes have similar concurrency, and not only for similar resource consumption. And also we optimize the procedures, introduce some catch and delay delete to make the peak is not very high. And the last one is the high density. And the high density is because our runtime technology makes the density could be reached very high, and maybe several hundred containers in one host. But at that time, the network part will have some overhead, and the OS agent itself introduce many overhead for that. So we avoid unnecessary parts and reduce the agent consumptions and optimize the part lookup, so we can. And we always use the newest version of the upstream to reduce the consumption and eliminate all the bugs. And that's what the challenges we face. And thank you all, and that's all.
The challenge of the OBS agent and the port lookup and so on. Have you considered pulling the neutron ports?
Sorry.
So in Kubernetes, that's the same as your neutron controller.
Yes.
So one thing that we found helps a lot for scale is to recreate the neutron ports ahead of time, and then we just, when containers are created, we assign those ports that already exist. And then when they are deleted, we don't delete the ports, we heat them up, and then we assign them to the next.
We do some of that, and especially for the containers, we'll restart it. So we'll keep some ports to delete. And but that's not all, can't solve all the problem, because if you have many parts in the same machine, that even the lookup will take more time, take a longer time.
The Asian communication. And the queues is still problematic.
Yes. Thank you. Okay, thank you.